say hello to everybody. I'm Cristiano De Nobili. I'm the lead AI scientist here at PySchool, and I want you to, let's say, welcome to our first tech talk of session 14 of the PySchool of AI. And today, it's a pleasure to host Norman Di Palo. He was part of the very first batch of the PySchool of AI. And after that, if I'm not wrong, then maybe Norman, you can tell us more. You also collaborated in I think, a couple of editions as a coach. Norman has been working with robots and AI for most of the last 10 years. He had the opportunity to conduct research at different institutions and companies across the globe, such as the Imperial College in London and also DeepMind as an intern. In today's talk, Norman will introduce large vision language models, generally referred as, let's say, foundational models. In particular, he will focus, he will discuss if we can use these tools as a brain of embodied agents and ground their thoughts into action executed in real world. He's going to present some recent results of his research performed at the Imperial College and Google DeepMind, and the design of, let's say, the next generation of robots, and give us a broader picture of the current state of the art in robots for everyday environments. So welcome again, Norman, and I want to leave the floor to you.
Thank you very much, Cristiano, for the introduction. Hi, everyone. I'm happy to be here virtually. Hope you're enjoying the School of AI, even if it is just started, right? So it.
Yeah, we are at the second week.
Second week. All right. Nice. It will pass by faster than you realize. So yeah. Anyway, yeah. Today I want to talk about the intersection between foundation models and robotics. If you're working in AI, you have an idea of what are foundation models. Everybody talks about large language models. And likely you also have an idea of like, what is a robot, even though it's probably not clear what these robots should do. Before I start diving into the research, a few words about me. I did my Bachelor of Science in Naples, Federico II. Then I did my Master of Science in Rome in AI and robotics. And now I'm doing a PhD in computer science at Imperial College London. Over the years, I worked for a few companies. Curious AI was a startup in Finland, in Helsinki, that was then acquired by Apple. The IIT in Italy, PySchool, and also translated. I spent quite a bit of time there. And also Google DeepMind. So let's start by specifying what I talk about when I talk about robotics. Sorry, there's a type. So as I was saying, we often have an idea of what a robot is, but nowadays robots are mostly useful in factories. So they can do like one thing forever, very precisely, but they are very bad at like dealing with uncertainties, unexpected events. So even something as simple as opening a door in an office or just like wiping a table in a coffee shop, for example. This is quite like unprecedented. Like, why is that? If you really think about it, we can all do these things. So why these robots struggle through that, considering that we have seen, we saw like AI programs doing much more difficult stuff. So you might wonder, ChatGPT just wrote my master thesis. How hard can it be? This is just a hypothesis. I did my master thesis before ChatGPT was a thing, so I'm not admitting nothing here. It is actually harder than it looks like, and it is very hard, unexpectedly so. It's so hard that it has its own paradox, something called the Moravec's paradox that you can find on Wikipedia. The Moravec paradox is the observation in AI and robotics that, contrary to traditional assumptions, reasoning requires very little computation. Well, this is not really true, but let's assume it does. But sensory motor and perception skills require enormous computational resources. The principle was articulated by a few guys and others in the 80s, and Moravec wrote in 1988, it is comparatively easy to make computers exhibit adult-level performance on intelligence tests or playing checkers, and difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. This was said in 88. It is even more true nowadays. So why is that? So to understand why, we need to do a dive into the history of AI. We do a very brief history of AI. So in the beginning, there was the abacus. So people realized it was interesting to count stuff, and this stuff could help you remember your results and do additions and subtractions and multiplications. One thing led to another, and we had the first computer. If you're ever in Pi school in the villa, you should recognize this computer. And so yeah, after that, then we had TPUs, so even faster computers. Why am I mentioning this? Well, you will see that the history of AI is very tied to the history of robotics, both in the sense of what succeeded and also in what failed. So after TPU, we stuck like thousands of TPUs together, and basically we ended up in the current situation. At the beginning, there was Deep Blue. So Deep Blue was the first AI program to beat Kasparov, a chess champion. And it was a historical match. It was the first time it happened. And it is interesting because Kasparov said that it was impossible that that was a computer. It must have been a human. And now we are kind of in the opposite situation. So when something is extremely good, we think it cannot be a human, it must be a computer. Anyway, how did Deep Blue work in a nutshell? It was called an expert system. So expert systems are built like this. So experts, human experts in the domain, write a lot of rules and stuff about a problem. Then a computer searches super fast for a solution. So in particular, what happened was they wrote the rules of chess, and then they wrote a lot of openings and closures. I think they're called like this, I'm not sure. And after giving these rules to the computer that experts knew about, so what is the best move to make at the beginning and at the end of a game in a certain situation, you then search. So you try all possible futures until you find the best solution. So can we apply it to robotics? Kind of. People try to write down rules on how to do stuff. It does not scale. Robots have to interact with possibly all the objects in the world. I didn't count them, but they are at least more than 10. So you cannot write rules for any object in existence, every door and things like that. So we had to think of something else. Let's go back to chess. So the next big opponent for AI was Go. The difference with Go, it's not intrinsically a harder game. The problem is what's called the search space. So in Go, at every turn, you can do many, many more moves than in chess. And this is very bad for a computer that wins by checking every possible future. Long story short, the approach that they did with Deep Blue did not work. The experts could not write enough rules, and the search was too slow to work. So what they had to do was kind of do the next thing in AI. It was giving machines a kind of intuition. And so AlphaGo was born. AlphaGo was this program developed by Google DeepMind that beat Lee Sedol in a historical match 4-1. How did it work? So the difference with respect to Deep Blue is that it wasn't just expert rules and search, there was also reinforcement learning. So an agent plays against itself in a virtual environment, obtaining a reward for winning. And eventually you scale it on thousands of TPUs and it solves Go. So it basically learns what are the best moves to do, and it comes up with solutions that no human thought before. And interestingly, this search and reinforcement learning plus neural networks demonstrated that it was possible to give to these machines a form of intuition. So we also try to apply this in robotics. Does it work? kind of. The problem is that reward functions in the real world must be hard-coded. So when you do Go, obviously you know if you won or not, so it's easy to get a reward. Also, Go is virtual, so you can play in simulation. But with robots, when training virtually, going to the real world is not trivial. And when you actually train in the real world, resets are time-consuming. Resets means maybe the robot failed through something and you have to reset the environment, put everything back to its place. It takes a lot of time. So also this thing was not the breakthrough we needed in robotics. Finally came the age of foundation models, of large vision language models. What is the difference here? So we saw that at first there were expert systems, then search with reinforcement learning. Now, what makes large language models actually work? The secret ingredient is self-supervised learning. So each single word on the web becomes training data. And eventually, the model becomes much smarter than expected. You simply take all the data you can find, you learn to predict the next word, and eventually you can solve all the stuff you can throw at ChatGPT. It's pretty amazing. Can we apply it to robotics? Kind of. There is no robotics data on the web, and collecting it is time-consuming, but we are trying. So language is plentiful on the web, not only for like data that was generated by the web for the web, but also all existing books that have been digitalized and stuff like that. So it looks like we need to collect a lot of data for robotics, right? But it's not easy because obviously it takes much more time than just trying to download and scrape the whole web. So here comes basically the core of this talk. So the intersection between robotics and foundation models. So these foundation models have demonstrated to have excellent reasoning capabilities. They can plan, they can reason, they have common knowledge, common sense, but they have no exposure to the real world. So they never tried to open a microwave. On the other hand, in robotics, we need to solve tasks with relatively little data with respect to these foundation models. And robots are very good at repeating a single thing forever, but lack this common sense that we really need. So how can we, let's say, take the best of both worlds? Robotics has not much data and high variety for everyday environments. Imagine all the possible offices, all the possible roads, schools, hospitals, houses. Foundation models have lots of data that leads to the emergence of common sense, but no real world experience, however. So I will talk about the last year or so of research that mostly I conducted between Imperial College London and Google DeepMind. And we will cover 4 main works that kind of cover some of the main trends in robotics and foundation models. The first part is using foundation models as a robot brain. It sounds easy, but we will see what I mean by that. The second is going beyond language and showing that there are also things called vision foundation models that are also extremely useful if any of you are working on computer vision. Finally, not finally, actually, third point, can large language models maneuver a robot? So they are very proficient in text, but can we actually give a language model the control of a robot and just say, do this task? How do they do? And finally, I will show how the community is trying to build robotics foundation models. So foundation models designed explicitly for robots. Let's start with the first one. If you have questions, you can stop me at any time, since the presentation could be a bit long. So feel free to raise your hand virtually or just say hi with your microphone. So the first paper is called Towards a Unified Agent with the Foundation Models. Normally, an agent receives an observation and then outputs an action. And in between, there's some sort of end-to-end policy that does that. This is true both for real-world agents, then, I don't know, virtual agents. Now, the point is, since it's quite hard to go from observations to actions, and we have a lot of language data that can do interesting stuff, can we do this? So can we have an intermediate representation in language space to go from observation to language and then to action? It sounds intriguing, so we try to do that. And to do that, you have to add some parts. So you need to go from vision to language, and to do that, you can use a vision language model. Then a language becomes basically your reasoning field. It becomes actually your brain. So a language model understands what's going on through text and decides then what to do. And this language is then grounded into actions through a language condition policy. The VLM that we use is called CLIP. CLIP is a contrastive model that has two branches. One is called an image encoder that takes images and outputs vectors of a certain dimension. It also has another branch called the text encoder that can take a sentence like the robot is grasping the red object and outputs a vector of the same dimension of the outputs of the image encoder. What's cool is that with these vectors, you can do a parallel dot product, and the results tell you how similar the sentence and the image are. So basically, does this sentence describe this image? This is trained on a huge amount of internet data where there are like captions that kind of describe photos. So this technique allows us to go from an image that the robot could see to actually a sentence. And this is the first example of how it can be useful. Imagine that in this simulated environment, you're trying to stack this red object on top of the blue object. When you try to learn this task from scratch, one problem is it's called the sparsity of the reward. So if you have a reward only for a successful episode, you may have very, very few rewards. So you may have, consider the robot starts from scratch, has no idea what objects are. So it just tries random actions until maybe every once in a whole day, it can do a successful stack. And it needs like thousands of successes to actually generalize. So the environment gives you very sparse rewards. If we actually take advantage of the capabilities of the foundation models, we can first go from this task that is given in language form to a plan of sub-goals. So to stack the red on the blue, we know that first what needs to happen is that the robot is grasping the red object, and then the red object is on top of the blue one. So we already have a better plan with respect to starting from scratch. And we can now use the VLM to analyze the similarity between these goals and each of these states or observations. What happens is that now you have an additional self-generated grasping reward. So now you don't have to do a successful grasp, a successful stack to learn something. Even a grasp gives you a signal to learn. And the interesting part is that these self-generated rewards happen, in this case, 20 times more often than the environment reward. So you are almost 20 times faster at learning at least a grasp. And once you learn to grasp the red object, obviously stacking it becomes easier because you start from a much better situation. And this is a very quick plot of the results. So what happens is that in blue we have this technique, and in orange we have a normal agent that doesn't take advantage of the foundation models. Vertical axis is success rate, horizontal axis is environment steps. You can see that there's a huge difference in learning speed. I will not go into detail on the results and plots for all the papers I mentioned. If you want, you can read the papers. I prefer to keep this talk like a bit more high level without going into details that can be boring. Another interesting thing is that you can now learn from a lot of offline data. So let's say that you have collected a lot of data for other tasks, and now you have this new task that is stacked the blue object on top of the red object. The language model breaks it down into sub-goals, as we saw before, and now you can extract and retrieve all the trajectories you have, even if they are not interesting. What happens is that a VLM can then check if any of the trajectories that you have retrieved are interesting for the task you are trying to do. And if it is, you can then add it to your new buffer. So you use as much as possible all the data that you have gathered for other tasks. We saw that one fundamental ingredient of language models is being able to learn from any data point, that is any token, any word on the internet. Well, this does not bring us at that level, but it certainly helps to make the most of offline data that might have been gathered for other tasks. So the steps are decompose the new task into text sub-goals, extract and relabel past data using the VLM, with the new language model extracted sub-goals, and then add all successful trajectories to a new buffer. This also unlocks learning from observation. So now you can even have a video of a human doing the task that you want to do. And the VLM can understand what's going on into this video. It understands that the human, it's first grasping the red object, and then it's stacking it on top of the blue object. Notice that it still calls it the robot because it is trained on this robot data. So it just thinks it's a different kind of robot in a certain sense. It's quite interesting. So then you have this list of sub-goals that is effectively a plan, and you can then execute it, and you have this one-shot learning from observation without having access to what actually happened in the video. So this was the first part, and the takeaway message is a unified framework based on VLMs and language models can tackle several reinforcement learning challenges that normally require separate vertically designed algorithms. So I showed you exploration, extraction from offline data, and learning from observation. Normally in the literature, these all require very different algorithms. Well, here we saw that with that framework that I showed at the beginning, observation, language, action, you can tackle most of this with a single algorithm. The second one is going beyond language, vision foundation models. This can, as I was saying, particularly useful for people working in computer vision. So this paper is called Dinobot. I worked on this with my supervisor, Edward Jones, at the Robot Learning Lab at Imperial College London. So as we said, there are two ingredients for effective deep learning: data and compute. And as I said, in robotics, what we lack is the data, but we have kind of the compute. So normally what we do is we take a pre-trained model from the internet, like a vision model, you know, those ResNets that are trained on ImageNet a few years ago, or the models that we'll talk about now. And we simply do what I was saying before. So we map an observation into a representation through this pre-trained model, then we have a learn policy, and then we output an action. And we just hope that as these pre-trained models, vision models get better, they will just extract better representations. Is this the best way to leverage vision foundation models? So like, can we just hammer them into our pipeline and will they work? Well, we show that there's a better way. In particular, we use Dino. Dino, it's a family of foundation models producing universal features suitable for image-level visual tasks, as well as pixel-level visual tasks. It is a model from Meta that has quite interesting results. So in this case, we are looking at a PCA representation of the features extracted on these images. They are grouped into 4 columns. And as you can see from the colors, all the interesting parts of an object are of the same color. So it generalizes to wings of animals and airplanes, elephants in very different views, and even a statue of kind of an elephant. Horses, even if they are very small, even there's lots of them, and cars, or at least like, car-like objects. We can then use this representation to like make a robot understand what are the commonalities between objects. So you don't have to retrain from scratch. For example, I will not go into detail, but very shortly what happens is you can give a demonstration, even a single demonstration, like how to grasp a can, and it immediately generalizes to a new can. For people that do not work in robotics, this is profoundly unremarkable. And it's tied to the paradox that I said at the beginning. For people that work in robotics, you understand that this is not as trivial as it looks like. In particular, what we do is, in each video here, we give a single demonstration on a particular object: a pan, a kettle, a cup, and a bottle. And then we can give to a robot a different object of the same class, and the robot generalizes immediately. We do this by leveraging these features that I talked about that are very consistent among objects of the same classes, the same class, or even other classes, as long as they share like common geometrical or semantic features. And so basically we have unlocked a very efficient way of doing reinforcement learning. Long story short, we do 15 tasks on 50 plus objects, and yeah, a robot can learn to do a lot of stuff very efficiently through imitation learning in this case. So you show the robot what you want to do, and it just emulates you in one shot. So this was the second part of the research, and the takeaway messages are two. The first is that foundation models are more than language. So everybody talks about language models, but there's more than that. This was a purely vision foundation model. There's no language whatsoever. The second is that we used to train networks to get good in-domain representation. I used to do this a lot. And now we have outstanding results from off-the-shelf foundation models. So in the future, I see training a network from scratch happening more and more rarely with respect to either taking an off-the-shelf model that it's extremely general or just fine-tuning one with just a handful of data points. The third part, it's a particularly interesting project that we did. So there was this ad that said, "Hey, ChatGPT, finish this building. Your skills are irreplaceable." So they were arguing that ChatGPT cannot do physical stuff, right? It cannot, do any manual labor. Is it true though? That's what we explored. So language model can solve intricate requests when it comes to language, but do they understand physical tasks? This paper explored this question. It's called Language Models as Zero-Shot Trajectory Generators. It was done by a colleague, Tae-Yoon Kwon, and I co-supervised this project at the Robot Learning Lab at Imperial College. All these videos are tackled by the robot, zero-shot. So we don't give demonstrations, it doesn't explore, it doesn't do anything. We just ask a large language model with a single task-agnostic prompt to solve this task with an off-the-shelf object detection model, nothing more than an object detection model. And we show that GPT-4, in this case, can indeed probably not finish this building, but it can surely be helpful. And again, this is completely zero-shot. So this is knowledge that GPT-4 already has in its weights, and it's quite remarkable. How it works is, from the top left, you have a task description, for example, shake the master bottle, that the user gives. And then we have a task agnostic prompt. What it means is that it's a single task, it's a single prompt that works on all the tasks. You don't have to change it. So it can just come, built into your robot. The language model then generates an internal plan on how to solve the task that you have asked. It can query this object detection model to understand where the objects are, because obviously language models cannot see. So that's the only thing that we have to add. And then it generates actually code to guide the robot. So this code generates low-level trajectories to maneuver the robot and solve the task. In particular, it can also track objects while the task is executed. In the top, you can see these 3 objects being tracked. And when the robot grasps the can on the left, its numbers that are the coordinate in the world change. What happens is that if we give the list of these coordinates changing to the language model in the bottom, we can ask, did the robot actually solve the task? So it not only knows how to solve it, but also if it succeeded or not, because a robot might have failed, and we need to know that. So what happens is that in this case, we ask the robot to pick up the ball. It tries the first time and it fails, but it realizes that it failed because it didn't see the ball moving with this pipeline. So it tries with a different grasp. In this case, it fails again, but it realizes that it has failed again. So it adapts its plan, another time until it has a successful grasp. And it realizes that it was a success and can go on with the next task. Interestingly, the final output of the language model is literally the low-level trajectory of the robot in numbers in the 3D world. We compared if it was better to have it actually as numbers, so as tokens that represent the numbers, or as code that then generates these numbers when executed. And the code was actually better. So GPT-4 can generate snippets of code that generate all the small movements that you have seen until the task has succeeded. It's open source. Take it for a spin if you want. I guess the presentation is being recorded, so you can go back to the slide and check it. We have all you need to try it on a simulated environment, and it's relatively easy also to try it on the real robot if you have one. Otherwise, you can just have fun trying to solve tasks in simulation, and let us know if it breaks at a certain point. I know it will break at a certain point, but I'm curious to see where. So this was the third part, and the takeaway message is, despite the lack of exposure to it, language models know quite a bit about the physical world and can tackle a series of tasks zero shot. So through reading the whole internet and more, they kind of developed also this ability to understand 3D trajectories. This is not enough to solve dexterous tasks or harder tasks, but it is certainly enough to solve a lot of zero-shot tasks for which you don't want to either give demonstrations or do reinforcement learning and stuff like that. The last part is actually building robotics foundation models, and I'll show what I mean. So language models were trained with a global indirect data effort. What I mean with data effort is that it is trained on the data that was generated by humanity over the last, well, probably the last 10 years, like exponentially overpower all the text that was created before. But you see the point. So it was kind of a global effort. Can we do the same for robotics? So what happened is tens of institutions around the world collaborated into this project about scaling up learning across many different robot types. So 33 academic labs, 22 different robots. We created what's called the OpenX embodiment dataset. It's basically made of lots of trajectories, lots of tasks that all these labs have recorded over the years. And we have almost millions of time steps. I realized that this is just like peanuts with respect to like GPT level datasets, but still we are going there. All the breakthroughs in deep learning were made possible by larger and larger datasets. ImageNet, CIFAR, whatever, lots of these datasets that created benchmarks that people could beat, and they could then understand how to create better algorithms and mostly also just add more data. These are some videos of these robots doing stuff. So we have all these kind of tasks. Most are like pick and place, but you also have cable routing in the bottom right, also opening stuff, moving objects like cleaning a table and all this stuff. Additionally, we use a model called RT2, which is the first example of what's called a vision language action model. So on the left, we have how you train a vision language model. So you have these internet scale images and their captions, basically, and you train something like Gemini or GPT to predict these sentences. So you get the image, you get the sentence, and you predict more tokens. What we did was then use this data to fine-tune this language model to actually predict movements as tokens, as if they were words, as if they were a new language. So controlling a robot as a new language, that is the language of translations and rotations. So now on the right of the image, you see RT2. You get a task as a text command. Then you take your image, you tokenize it, and you pass it through a VAT, and you have these tokens that are both language and vision. And then you have this huge vision language action model that predicts the next tokens. While normally it will predict text, in this case, the tokens are this actions language that you then execute on the robot. And long story short, by adding basically all the data from the internet for the vision language model and all this huge data set for robotics, we have an incredible increase in performance. So these models are really learning in an extremely multimodal way. So like random images from the internet are actually improving the common sense ability of the robot, its ability to recognize image, understand situations. And the huge data set of robotics interactions ground this knowledge into actions, making it learn this effectively new language, which is the language of actions. Also, it's all open, it's downloadable, and there are some pre-trained models. If any of you works in robotics, this is a pretty cool project. There are some Colab notebooks where you can just explore the data. Yeah, I think this is very, very cool, and the whole community is pretty excited about this. many people think that lots of data is probably one of the very few ways to make robotics work. And so somebody has got to collect this data. The takeaway message here is deep learning needs lots of data, and with a global effort, we can gather enough to train the robots of the future. These were the 4 main works that I wanted to discuss that cover many aspects of what's going on in today's robotics. The first one is how to unify reasoning through foundation models to have a single agent that can do a lot of things in reinforcement learning. Second part is vision foundation models. Maybe some of you were not aware of vision foundation models. You can download them for free. They're super easy. You can go on Hugging Face, and there are like 10 lines of code to use them. Also, language models. ChatGPT is doing homework for lots of kids. Maybe in the future, can also maneuver robots. Maybe ChatGPT, maybe Gemini. We'll see. And finally, how to actually build other foundation models for robotics by combining the vision language models that are already out there with these huge data sets of robotic actions that are normally not on the internet. This was faster than expected, but I didn't want to overload you with information, so I'm happy to have a chat now. Thank you very much. This is my Hex handle. Happy to take questions.
So thank you so much, Norman. It was super interesting, this overview. And
thank you.
Yes, we heard a lot about large language models, but not so much about vision large language models. So vision large models, you call them. So if there are any questions, feel free to unmute yourself. Norman is available to reply. So feel free to unmute yourself or write it in the chat. So Ahmad, you are the first one. Go ahead.
Nice talk, Norman. I wanted to ask the question that, like in LLMs, the biggest self-supervised pre-training task is next word prediction. So is there any task that has proven to be really good for robotics for pre-training part, or because the data set that you shared, it had a lot of tasks, but is there a specific technique that works really well for robotics?
So interestingly, as I show with RT2, the exact same techniques from language modeling work very well. You have probably seen in the last few years a convergence of deep learning into transformers that are sequence-to-sequence models. So as I was saying, instead of having a new task, you basically transform the robotics task into something that looks like language. So you encode actions as a new language, so the language of rotations and positions, displacements, translations. So you effectively have your input sequence is the language, or the task in natural language, the tokens from the vision to understand what you're looking at, and possibly the past actions that you have executed. And so you learn this language that says, okay, if these are the previous tokens and I have done the actions, what are the next actions? Just like you learn, if I have pronounced these words, what are likely to be the next words? You now say, if I have executed these actions, what are likely the next actions?
Go, Kandal, is your turn. Go ahead.
Hi, Norman.
Hey.
Nice talk. So I was wondering, how do you deal with, let's say, the common pitfalls that we see with these large language models? Let's say hallucinations, and so how to deal with them when you're dealing with robots?
Yeah, that's a good point. Long story short, there's no real difference with how you deal with them in normal natural language processing. The advantage is that in robotics, the language itself, it's quite easier than what we are used to for language models. So language models now have to solve very difficult language tasks that are basically human level intelligence, while the language part for robotics is rarely harder than Grammy, a Coke. So one difference in robotics, it's that you don't really have in language is called the distribution shift. In language, when you predict the new token, that becomes your past experience, right? So you basically have perfect control over your input and output in a certain sense. In robotics, when I talk about this language of actions, it's not that easy because the next token, that is the next action, it's executed, and what will happen in the real world is unpredictable. So that's actually the real problem that we deal with in robotics. So if you do a few wrong actions, the future that you experience can be dramatically different. Let's say you're grasping again this Coke, you slightly open your gripper and then it falls on the floor and it spills Coke all over the floor. A few wrong tokens brought you into an unpredictable future. So now your policy has to adapt a lot. So this is what's called the distribution shift, the state action distribution shift, and that's probably one of the most important problems. One way in which we tackle this is by giving at least a robot the ability to understand what they don't understand. So if they realize that there is an unexpected situation, they can stop and ask for help. Because if you don't ask for help, sometimes you just make things worse. Like imagine, again, you drop this Coke and then you just walk over it and then walk through the house and you basically made a mess. So at least if you can understand that you need to stop and ask for help, that's better. Yeah, there's a very cool paper called Robots That Ask for Help that was nominated as one of the best papers of this year conference on robot learning, which is the top tier conference in this field. If you're curious, that's a very interesting paper.
Cool. Also, it's like, is the reinforcement learning still playing a large role in the learning with large language models coming into the picture? Is a different way of reinforcement learning we are trying to use, or it's still the same that we did for, let's say, AlphaGo or something like that?
Interestingly, reinforcement learning now plays a huge role in language models themselves. So I don't know how familiar you are, but yeah, the whole alignment part, it's based on that. In robotics, it's less important than it used to be, because again, as I discussed, there was this wave of reinforcement learning after AlphaGo, after the Atari benchmark. Everybody tried to do reinforcement learning on robots. It didn't really work. Because again, it takes too much time, and people realize if it's gonna take so much time, and I still have to be there in the room fixing the mess that the robot has done, I might as well just give you a demonstration. So I might as well just shift from reinforcement learning to supervised learning. So what's happening now is that the main flavor, I will say, of reinforcement learning is called offline reinforcement learning, which is the version of reinforcement learning that looks the most like supervised learning. Long story short, what's likely to be the secret recipe is a lot of imitation learning and then some small reinforcement learning on top of that after a robot has grasped most of the situation. There are some things you cannot teach through just imitation, but yeah, I think it's gonna be like the cherry on top, reinforcement learning that can give the final jump in performance, but most of it is probably going to be imitation learning.
Okay, thanks.
Sure.
Hi. So in RL setup, can we also use language models to generate better reward functions? Can we design some adaptive reward functions using language models so that our tasks can be improved over the time?
100%. That's also an interesting area of research. Let me give you a second. Sorry, give me a second. Let me find you a paper. Yeah, I'll drop it here. So there's this paper called Eureka from NVIDIA that does something like that. So the language model defines a reward function that you can then use to optimize your reinforcement learning algorithm. It is an interesting approach. There are some reasons why it's not super scalable, in the sense that it assumes that you have a simulator, so you have access to all the low-level state of the word, which is not true. Oftentimes, if you want to deal with the real world, what I'm trying to do is like the first paper that I mentioned. So having a language model telling you what are the sub-goals, and a visual language model telling you if you have reached those sub-goals to get a more dense or at least less sparse reward. But yeah, that's a very active research area.
Yeah, thank you. One more thing. When we talk about representation, can we also use some better 3D representation like SDF, or maybe nowadays NERF is being used to represent 3D word? Can we use language model to navigate a robot in the NERF setting as well?
Also, yeah, absolutely. Yeah, I'll give you another paper since you're curious. I think this is another interesting paper where they basically use a NERF to build a 3D environment. So you move around with your phone, you record a video of the environment, and then it just becomes a NERF where an agent can walk through it in simulation without actually having to walk through it. And so after training in this NERF, like an hallucination, like a dream world, it can then transfer to the real world. So yeah, using 3D representations is also extremely interesting. There's a lot of research on NERF, Gaussian splatting. So yeah, that's also an active area of research.
Thank you. Yeah, Vijay, I have seen this paper. I was wondering if we can use NERF for navigation as well. So yeah, thank you.
Sure.
I wanted to ask another question. You mentioned that in language models and in robots that we kind of keep the record of what the action has produced. So the first question is that like for every token or for every action that has been produced, for how long do we for how long that a robot is keeping making it like keeping track of it, that what it has done in past. And secondly, like is it kind of an incremental learning and updating itself in real time, updating the weights, or is it just like the previous context that it has run?
So regarding the first part, how much context to keep track of, it's an interesting point. One of the main weaknesses of transformers, at least the basic version of transformers, is that they scale quadratically to the number of inputs. So the more inputs you have, the slower it will be. Models like, again, ChatGPT works. They look so fast because they use a lot of compute, but transformers are actually quite slow for this. It is an interesting question because normally for many tasks, a robot has to just keep track of the immediate past. But it's also true that when you are interacting in an environment like your own house, if you want to, I don't know, grasp something like a pair of shoes, you generally remember where you put them, but it would be unreasonable to just have the whole day of memories in context as visual tokens. So what's happening now, it's something called retrieval augmentation, where you basically have an external memory module and a robot can decide to write some interesting information. So if something interesting happened, you can just write it there. And then if you need something in the future, you can just try to retrieve from this buffer. There was a paper called Token Turing Machines that does something like that. But yeah, this idea of like a fast dynamic memory and like a longer but slower memory, it's also interesting, yeah. Sorry, the second one was the continual part. Continual learning is also very interesting. There's a lot of research on this. The problem is that it's super expensive to train these visual language models. So normally what happens is that you collect data over weeks or months, and every few months you may do a new retraining. Doing actual continual learning is not easy for these reasons. But yeah, people are trying. There are conferences that are just dedicated to continual learning. It's an interesting aspect.
Maybe I can go next. Thank you, Norman, for that great talk. I have a question. Most of my reading in robotics has been mostly around autonomous driving, and I've seen two kinds of papers in this particular realm, even for, end-to-end trajectory prediction. One is to pass the raw pixels of an image to a multimodal LLM and have it, give you the output trajectory using the vision language combination. So, and the second one is to use external tools. So I think even NVIDIA released a paper very recently on that, where you have, it's taking one of the CVPR papers, like occupancy networks, mapping, and segmentation models, using them as tools, and then only taking the output of those as language and then giving you the trajectory. Do you have any idea which of these could work better, and why would you choose one or the other?
Yeah, this is a recurring question in deep learning. Deep learning historically had incorporated all external modules into a single end-to-end network, because as it is clear, the more inductive biases you add, the more efficient you are in learning, but the less you can scale. So it all comes down to how much data you have. Waymo, for example, a former company from Google, has 3D maps of environments. So it can only run in selected cities because they have an accurate 3D map of the city. What happens is that it allows you to deploy immediately. So you can go on the road relatively fast. With respect to Tesla, which is trying to do end-to-end, with the disadvantage that you cannot, the self-driving thing, it's kind of working. I'm not an expert, but the disadvantage is that you are not as safe as Waymo, where you don't even sit at the wheel. While in Tesla cars, you always have to have your hands on the wheel, but you have the long-term plan of scaling to everything. So you're not restricted. So I think it comes down to, it's ultimately almost a business decision. I believe just end-to-end models will probably win. Although for driving, there are some external modules that can always be useful. For example, just detecting road signals, that can always be useful. But yeah, it just depends on how much data you have, I would say. And so the data you have becomes the business you're trying to build. And it's an open question.
Thank you.
Sure.
So, if there are no other questions, I thank you again, Norman. It was super interesting. And also the question time, I hope was fruitful for everybody. So you have Norman contacted. So if you have a further question, feel free to ask him. I think he will be happy, will be glad to reply you. And thank you again, Norman, and thank you
very much.
Everybody.
Thank you for having me.
For being here, and see you at the next Tech Talk at 5 School.
Enjoy the School of AI. See you everyone. Bye.
Thank you.